So I wanted to talk about these three topics, and there seems like there's a lot of confusion or a lack of clarity around these topics, and I'm not sure that needs to be the case. And I think in some cases it almost seems to be deliberate. So this is the idea with this is kind of it just will hopefully leave you a little bit more informed about what these three things are and what the difference between them are. That was the more concise title of the talk. Oh, it is an audience participation talk, so you're forewarned. So I was going to quickly just kind of try and define a few things, talk about some main concepts, and then just go through some obvious confusions. Look more closely at data science, and in particular look at how machine learning works, and then talk about how those translate to a few use cases. So with any talk like this, the first thing is to put a slide up which talks about the transformative power of AI, etc., etc. We stick in a self-driving car, Alexa gets a show. There's always got to be an IBM Watson there, and you've got to have something about Google Translate. You also have to stick a robot in, God knows why. And for some reason, it baffles me, you've got to have a printed circuit board representation of the human brain, preferably in blue neon. As if that wasn't patronising enough, you then have to have a picture of Arnold Schwarzenegger and tell the audience that Skynet isn't going to happen. The problem with stuff like this is it kind of... oh, by the way, this is the first question. Does anybody know who this character is? From? He was actually the prototype Tin Man for Hollywood blockbuster The Wizard of Oz, and he had to be replaced due to smoking-related illnesses. So, more interesting than talking about this kind of standard AI slide is thinking about what people think about AI. So if you think about people being on this kind of spectrum, where the left-hand side is like people seeing it as just, the latest snake oil, and the right-hand side is those people that do buy into it. And these are kind of blockchain terms, fear, uncertainty, and doubt drives people towards like a sort of traditional mindset, and then fear of missing out means people are desperately trying to jump on the bandwagon. So you could think about these people over here as being rational skeptics, which would be a positive way to see them, or you could think of them as just plain Luddites. And then these people over here, you could see them as being tech savvy, they've seen this emerging technology, they've got in there, or they're just gullible. So reality lies somewhere between these two, somewhere along this spectrum. So I guess everybody in this room is going to be situated somewhere along this spectrum. So this is the audience participation bit. So I'm going to slide the cursor along here, and you're going to stick your hand up when I get to the bit along this continuum that represents you. So, right, we're starting off with complete snake oil. Moving further along. Come on. A little bit more. And then tech-savvy type crowd. All right, OK, so there seems to be more people at that end, and I did see a few hands going up right at that end. Not normally distributed, but that's kind of what I expected coming to Leeds. My take on this is probably much the same as the audience. I'm somewhere around here because I still sort of follow the stuff that's coming out of academia. What's going on in academia now with this kind of stuff is the whole process is now bypassing the usual kind of submit to journal, do your peer review stuff. It seems to go on to things like archive, and the biggest papers now are going straight onto archive without any of that sort of process, which is a good and a bad thing. But it kind of highlights the speed that things are moving at, and the sort of rate at which new discoveries and developments are occurring is so fast, and it's fast in a way that surprises the people that are actually working in it. What we've got at the moment, though, is there's a big skills gap between the stuff that's being done in academia and where we are in industry, and when that skills gap gets backfilled, I think the transition of the cutting-edge stuff that's being done in academia will move into industry a bit quicker. So I think we're going to see quite a bit more than where we currently are at the moment. So that's why I lie there. Very simply, the relationship between these three is like this. Artificial intelligence encompasses data science. Machine learning is a subset of data science. And if you're interested in deep learning, that's a subset of machine learning. If you keep this framework in mind, you're not going to go far wrong with this. So with that said, we'll have a closer look now at data science, and you can't really do that without talking about machine learning. So machine learning is a mathematical topic, mathematical statistical, and it's concerned with the optimization of algorithms. And it's a bit like a car engine. It's a brilliant piece of engineering in its own right, but it can't really do much by itself. So this is where all these other technologies come in. So once you have machine learning with things like data wrangling, model evaluation, image handling, natural language processing, you've then got data science. And why should we be interested in data science? Well, mainly because of impact. And I don't mean impact in terms of that kind of slick jargon type way you see on all like the business promotional material. I mean specifically actionable insights which lead to outcomes. And actionable is the key word there. So if you say to someone, your fly is undone, that's actionable. If you say to someone, you're going bold, that's not actionable. So this is about making decisions. And just to kind of drive that message home, there's a few examples here. So a classic early example is Moneyball. So this was the story of Billy Beane, who's the manager of the Oakland Athletics football team, that's American football team that's struggling. So he brings in this Harvard economist who uses kind of early data science techniques and changes the way they select players. They look for attributes in players which are undervalued by most teams. And they select on that basis, and they go on to make baseball history. Netflix, again, here, there was a data scientific approach, and they identified that people that enjoyed the original BBC TV miniseries House of Cards were also fans of David Fincher, the director, and Kevin Spacey. And they went on to make House of Cards, which has been massive. So the actionable here, they changed the way that they develop programs. Crime forecasting in Memphis, this was the Blue Crush approach. They used a data scientific approach to change the way they deployed police on the streets, and it return on investment 860%, murder rate reduced by 35%. Zurich Insurance used a data scientific approach to classify injury reports and massively reduce the turnaround time. So again, the actionable here is in this case slightly different because it's changing the way they do business. So our next question, does anybody know who played the Harvard economist in the film? Oh, close. He played the manager. It was Jonah Hill in an unconventional role for him. Why not data science? So, well, data science is not the answer to every problem. It is the answer in some cases, and in those cases, it really can be transformative. And the biggest challenge for data science now is, can anybody tell me what the biggest challenge is? A lot of people say skills shortage. I think it's getting the right use cases. So DJ Patel has said something about this. He was Obama's chief data scientist, and he was saying that people can't identify use cases. And the reason that I think we struggle to find use cases is because people don't know how data science works. And also, they focus on the solution they want to use. So everybody's talking about AI. Everybody wants to get AI into their business to solve a solution, but they don't really know what solution they're going to solve. So they're almost working the wrong way around. They're looking at the solution without having identified the problem. And this boils down to the hype around the subject. So we really need to kind of get this hype under control a little bit and start talking a bit more rationally about these kind of things. And I think this is the area where I'd like to make a bit of an impact. So trying to just help people understand and try and eliminate the hype, or minimize it anyway. So as I said, there's a lot of confusion around this area, but there are some things that are classic confusions that crop up time and time again. AI is a horrendously unfortunate term. It was coined by John McCarthy in the 1950s. Nobody agreed on what intelligence was back then. They've been arguing over it for 200 years, and John McCarthy decides he wants to create an artificial version of it. So he's cursed the field ever since with the need to try and explain what this is. I think the other thing about AI that you probably need to bear in mind is it's a moving goalpost. So 50 years ago, people would have thought a computer that could play chess was artificial intelligence, and I guess this is probably 30 years old now, and nobody would even dream that that's anything to do with artificial intelligence. Data science is not big data. You can do data science on small data. The combination of big data and data science is really powerful, but it's not essential. Data science is not databases. Lots of data scientists know nothing about databases. And data science is not data analysis. Data analysis is identifying trends in the data Data science is building models to make predictions around individuals. Another way of looking at that is data analysis this isn't supposed to offend any data analysts in the room, but this is about hindsight, and data science is about foresight. And anybody that says data science is all things data is setting you up for a major fail. Machine learning and data science are not the same thing. As I said before, machine learning is the engine of data science, or if you prefer, data science is just applied machine learning. And this might be a bit hard to say, but the fourth point was actually a more important one, which is that AI or machine learning in business in 2018 is, does anybody know what it is? It's data science. You'll find some people that will argue with this. You'll find some niche areas in academia where you could dispute this. But in 2018, probably out for at least the next 5 years, this is going to hold. AI is simply data science. Whether you're working with images, language processing, it all boils down to numbers and finding patterns in that data. So I'm going to put this slide up, and if you realise what the slide is, shout out, please. So here's a wiggly line. Here's a few dates along the bottom, 1975 and 1990, where the dips are. 2018, present time. That's a typical day up at my gaff in Mosley. There's an image from the Game of Thrones. Any guesses? Here's a more explicit image. These are the two dips, and these are the AI winters. So the AI winters occurred when the expectation around AI was so high that reality couldn't possibly live up to it. And what happened was people grew jaded with it, and there was a complete collapse in funding. So research departments were shut down, careers were destroyed, people lost their jobs. Research basically, completely dried up. The only way to get stuff published was to call it something different, like machine learning or informatics or statistical modeling or statistical learning or something like that. The question then is, we're at 2018, what happens next? So companies that are selling AI would probably have you believe that this is going to happen, it's going to take off exponentially. I think Theresa May said this a couple of months ago when she had time on her hands to think about other things. And the media obviously is very much kind of looking at this kind of thing. Maybe it'll do that, maybe it'll just kind of level out, or maybe we'll have another AI winter. This guy is Neil Lawrence. He is the chair of computer science and neuroscience at Sheffield University. He's also the head of machine learning at Amazon in Cambridge, which makes him the head of machine learning at Amazon UK. So he said that the next AI winter is going to be 2019, next year. And this isn't an ivory tower academic. This is a guy with his finger on the pulse. He doesn't just work in industry. He's involved in organising conferences, and he has his fingers in a lot of pies. So it's quite a bold and striking statement. And any guesses as to the biggest cause of AI winters? Yeah, it's hype. Number one cause of AI winters is hype. So don't believe the hype. Yeah, so I think the message here is, treat some of this stuff with a degree of healthy skepticism, because some of it is undoubtedly overinflated. I think the more you hear people using terms like AI rather than data science or something specific like image processing, the more likely it is that they're probably trying to, boost it a little bit. So let's dive right in now to how machine learning works. So I've been told that if I say this word, half of the audience will instantly go to sleep. So I thought I'd better find something that unites us in a common sort of cynicism of this word. And this is George Box, and he said, all models are wrong. That's the M word, by the way, model. But some models are useful. And this is a great quote. Anybody doing data science should have this in their minds at all times. The problem with this word is people bandy it around. It's another word that gets sort of chucked around, and people don't actually say what they mean by it. And I think it becomes confusing because it's used in so many different places. And you can have different sorts of models, but the essence of it is that it's just a simplified version of reality. So if I draw you like a box with a triangle on the top and a chimney, like another rectangle and a squiggly thing, that's like a representation of a house, and anybody would get it. It's just a simplified version. Technically, you would call it an abstracted version of reality. This is a model, Model Spitfire. This girl's, is it useful? George Boxey's sort of comment, yeah, it's useful. This girl's getting a lot of value out of it. It's got a propeller, it's got wings. Can it fly? No, it's an abstracted version of reality. Lego Einstein. Is it useful? Yes, it's got aesthetic value. This girl's enjoying it. Can it come up with a general theory of relativity? No, it's an abstracted version of reality. These are models, abstracted versions of reality. No scars, no blemishes, no hang-ups. They don't have the sort of clothes you need to survive in Leeds in the autumn or the summer. They're abstracted versions of reality. And this is an abstracted version of reality. This is a model. If you poke or prod this model hard enough, it'll fall over. But generally speaking, it's a useful model. So now let's talk about models and data. So I've been around this room, I've asked 25 people how tall they are and what the shoe size is, and I plotted each of these individuals out, which is one of these data points. So now I have this mental model in my head that bigger people have got bigger feet. Can we make that more explicit? Yeah, we can make a mathematical model and then we can write it down so it's no longer just something I've got in my head. We use the equation for a straight line and we say that the gradient is 0.15 and the intercept is minus 17, which you'd see if the scale went to 0. Does that model fit the data? Not perfectly, no. It's going back to that quote, you know, all models are wrong, but some models are useful. This does give us use because we can see that somebody who's at 190 centimetres is probably going to be between 10 and 8 shoe size, but they're not going to be down here. So it has value, but it also has error due to variability. So we've just built a model with one feature. Using this equation, we've got height. We're using height to predict shoe size. We need to figure out this value and that value. We can build a model with two features, and if we did this, we might be able to get a more accurate prediction of shoe size. Maybe we could use height and weight, in which case we'd need to find this value, the coefficient for height, and we'd also need to find the coefficient for weight, and we need to find this value C. And this basically is what machine learning does. It's just a way of figuring out what the values are in a big equation that allows you to predict things. So we learn those parameter values, those weights, using machine learning. So the general approach in machine learning is you train a model using what we call labeled data. These are X values where we know the Y values. And then once we've built that model, we can use it to make predictions for X values where we don't have Y values. So here we've got two microscope slides taken from breast tissue biopsy samples. The biopsy is taken, they put it on a slide, they stain it up to make the nuclei stand out, and here you can see the nuclei for a benign diagnosed biopsy, and here you can see the nuclei for a malignant biopsy, and you can see they're clearly different. And we can describe those kind of differences using features like radius, texture, how big the perimeter is, how smooth the perimeter is. So this isn't a lot different to the equation we saw before. Before we had height and weight to predict shoe size. Now we've got radius, texture, perimeter, area, and smoothness, so 5 attributes or features, and we're predicting whether it's malignant or benign. So we have an equation with 5 bits in it, and we're trying to make a prediction for Y. And each of these 5 bits need that coefficient that we've got to calculate machine learning. So we need to build a model. And this model is built in an iterative way. You imagine a supervisor that stands over this process. You've got your machine learning algorithm, it's up and running, and it comes up with a coefficient for this one, a coefficient for this one. There might just be random numbers to start with, and the supervisor says, no, you've predicted this incorrectly. You predicted no, it should be yes. Go back, tweak those coefficients a little bit and see if you can get the right value. So eventually it'll produce the right value, and then it'll go on to step 2. And see if it gets the right value there. And if it can't, the supervisor said, go back, tweak your coefficients and see if you can get the right value this time around. And working through this process, you hope you'll reach a point where for each of these 8 patients, you'll get the correct diagnosis. And then you've got your model. And then you can take your model to a couple of samples where you actually don't have Y values. So the pathologist's not around, you know these values, but you can't make any prediction. But you can use this model that you've built, and that is able to give you the prediction. So that is essentially what machine learning does. It's just working on data tables. It would be nice to say that was the end of machine learning, but you will come across supervised and unsupervised. So it's important to just kind of say what they are. What I just talked about is making predictions. You can make predictions in terms of predicting values or, numbers, and we call that regression. And you can also predict whether something is going to be in a red, green, or blue category, or whether it's going to be benign or malignant, or maybe benign, malignant, or refer to pathologist for further investigation. So they are supervised learning, and you can probably see I've focused on that idea of a supervisor during the training that uses the Y values to help build the algorithm. You can also use an approach where there aren't any Y values. You've just got kind of data, and you need to look for patterns in it, and that's what we call clustering. And here we're looking at data points that are similar to other data points, and are there clumps in that data rather than just being sort of dispersed throughout a space. Here we've just coloured them to make the separation clear, and that's called unsupervised learning. So I'm just going to talk you through some use cases now: simple, complex, and cutting edge. So simple or classical use cases. PricewaterhouseCoopers recently demonstrated this algorithm they'd built to predict the waiting times at a couple of hospitals at the A&E department. They were trying to help the hospital not go above the 4-hour waiting time for which they get fined, penalised. So, can anybody tell me what approach they would use here? We're trying to predict waiting times. Would it be clustering, looking for patterns in the data? Would it be regression, where we're looking to predict values? Or would it be classification, where we're looking to predict categories? Regression, yeah. And if you think back to the data table that I showed you before, what would be along the rows? Yeah, patients. And what sort of things might you have as your column headings to predict waiting times? What kind of things might make waiting times longer or shorter? Yep. 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 So some of the things they looked at were age, the arrival method, whether they came in an ambulance or a car, time of day, health condition, pain assessment. Second example, Hewlett-Packard predicted the flight risk for each of their employees. This was famous and then infamous when it ended up all over the newspapers. So they were predicting the likelihood of each of their employees leaving, whether they fell into the low, medium, or high risk category. So what approach would we be using here? Would it be regression, clustering, classification? Classification. We're looking for categories. And what would be in the rows? Yep. And what sort of things might we use to predict whether someone's likely to leave? Yep. Salary, raises, job ratings, time position, time since last promotion, commute time. Last one. So Netflix use a recommender system, and if we just think about recommending movies based on the similarity of your profile to other people's profiles, what's that approach? Yeah, it's clustering, because you're looking at the similarity. And what's in the rows? Yeah, user profiles. And the columns, what kind of things might be used to predict? Yeah, genres, directors, that kind of stuff. So some more interesting use cases. This is a phone app developed in, I think it was the Netherlands, and you can hold the phone against your arm and it'll take a photo of a mole and it will predict whether it's fine or whether you need to go and see a GP. It also monitors it over time. This one is really interesting piece of work done between IBM and Columbia University. And they were able to predict the onset of psychosis in at-risk individuals over a period of several years. It was 100% accurate. And they did this by recording free speech, of people's free speech, and analysing it. And the things that were able to predict the onset of schizophrenia were things like excessive use of first-person pronouns, excessive use of which, the language structures. So 100% accuracy, even over a small data size. And this one, ScreenX, they used a machine learning approach to identify factors which indicated non-adherence to drug treatment. So this is a big problem in the States. They reckon 125 deaths a year, and the costs are into tens of billions. And they found things like if your partner was likely to adhere to the drug program, you were. If you had young children, you were less likely to adhere to following the drug treatment all the way through. And a really interesting one is if it's a male patient and a female doctor, a male patient is less likely to stick to the drug treatment. So the more cutting edge stuff, this was a data science conference in Manchester earlier this year. It was delegates from all over the world, and it was academia and industry. It involved organisations like Office of National Statistics, the UN, Royal Statistical Society. BGSS sponsored it. Autotrade also sponsored it, but they took the opportunity of using this page as a job advert, which is interesting. There's a few sample papers, and it just gives you an indication of the diversity of the people presenting and also the kind of stuff they're doing. So forecasting US elections, tracking fever in Rio de Janeiro, humanitarian applications, and citizen science. So a couple of particularly interesting things. Microsoft have got a big program where they're trying to develop, they're trying to use AI for healthcare and improve the social good, so to speak. What does AI mean here? We'll say data science. I hope so. Right. Yeah, it's data science. They're just working with numbers. The last that was presenting this was she was looking at asthma, and she saw asthma as not being a single disease. She was trying to demonstrate that it's a number of diseases, that they're basically 5 different diseases. So it's a bit like the clustering image that I showed earlier. If you could find some way of separating out all the different factors, you might find different diseases. And this is actually what she found. She found sort of 5 different versions of asthma. And she also challenged this idea that there is an allergic march, that if you have eczema as a child, you go on to develop asthma as an adult. And she found that the evidence for that was a little bit lacking. This was a paper actually co-authored by Hannah Fry. And this idea here is that if you have a burglary at this point here, that the likelihood of there being a repeat burglary the following night is high there, and then it kind of diminishes the further out you get in that circle. So that's an old theory. But this guy was saying, what happens if there's a railway or a river there? So you've got to take that into account. And you've also got to take into account what we know about, the behaviour around crime. And he was saying that you need to merge these kind of circles with street maps and other features and understand this kind of stuff. So that was quite interesting. I'm really interested in how networks affect behaviour, so I like that. This guy was talking about veteran suicide in the States. This guy was attaching sensors to people in hospitals and monitoring the interactions between doctors, children, nurses, parents, auxiliaries. He did the same thing in a school and managed to find a way so that when an epidemic hit a school, you didn't have to shut the whole school down, which is really expensive. You could just find the particular classroom that was crucial to the spread of the disease and shut that one down. Saved a load of money. So this is the last thing I wanted to talk about really this evening. This guy, Valid Magdi, presented some interesting stuff. So this was post the Paris attacks. There were lots of Islamophobic comments posted in various papers. And he was saying these were comments from people that hadn't previously in their social media demonstrated any kind of tendency towards Islamophobia. But he said this was predictable. He said you could go back, mask the data, and effectively you could see this was going to happen by looking at what groups they were involved with. And interestingly, these are the kind of characteristics which those people that were attacking Muslims were denoted by. This is probably not surprising. Donald Trump, NFL, Fox News. And these people fell into the sort of the role of defending Muslims. There's some interesting stuff here. Electronic dance music, the National Rifle Organisation. I find that surprising. And this is the last bit of the talk. This is the same guy, and he was talking about this particular paper he'd published called "Fishing, Fake It Till You Make It: Fishing for Catfishes." So, do people know what a catfish is? I don't mean the fish. A catfish is someone who pretends to be something that they're not on social media. So, can you give me examples of social media where you find catfishes? Online dating, Facebook, LinkedIn is 100% catfishes. What he wanted to do was automatically identify fake users on social network sites based on user profiles. What would be the best site to find catfishes on? Twitter. No Facebook. Apparently, Pornhub is a pretty good site to go fishing for them on. And Pornhub is an adult education site. There are apparently 100,000 user accounts on it, and 5% of those are verified. So you've got a way of building up a profile of people where you do actually know who they are. And the number of people they got here was enough to give them confidence that they could actually compare that profile against other people and see if they were telling the truth in the other 195,000, see if they were saying things that were actually true about themselves. And what they found was that 25% of people are likely to be lying about their age. Males were pretending to be young females. Females were pretending to be older males. And male liars were generally older than female liars. So that's the lesson from that. From your online public social activity, hidden personal information can be determined, or estimated, not determined. The BBC got wind of this after he presented it at a conference in Australia, and he tweeted this kind of report from the BBC. Pornhub must have spotted it and got in touch with him and said, can you send us this publication? So he said Pornhub now follow him on Twitter, which takes some explaining. So there you go. Thanks for your attention, and if you have any questions.